in this application, another two-body problem is related to two masses. One is moving along a frictionless incline, and this mass is M2 is 6 kilogram, and the other mass is in a vertical position with 2 kilogram. The two masses are connected by a light string, and moving over this string is passage over a frictionless pulley, and the driving force is related with the component of the weight of the mass 2. And you should draw your free body diagram for the both objects. And also you need to find the magnitude of acceleration of these two objects. As we said before, in this kind of problems, the two objects will have a common acceleration. It's the same, and the line of motion is the same. It's considered as positive as we demonstrated in the previous example. And again, you need to find also the tension of the string. Moreover, in part D, you need to find the speed of each object when the system is released from rest. That is, the initial velocity or the initial speed for each mass is considered as 0. And then again, you have to find the speed 2 seconds later from the start of motion. The angle of the incline is given as 35 degrees. This is the free body diagram for the first mass 1, which is along the y-axis. We have two forces, the tension upward and the weight of the object downward, while the second object, M2, sliding down the incline. As we suggested before, it's better to draw the x-axis along the line, and that's what we have done here. This is the free body diagram, shows that the x-axis is in this direction, and in the positive direction we're going to consider positive acceleration in this direction. This is because the driving force is going to be by M2g, or the component of the weight of M2g, this component here. So and also we will have along the x-axis the tension in the rope, where this tension is trying to prevent the force or the component of the weight along the x-axis to move. This tension in magnitude is the same as this one, but as you see in this case, the tension is upward, because the tension will overcome the weight if the object of the system will move with an acceleration in this direction. So in this case, we have two body diagrams, and from these body diagrams we can get three equations. One for the first mass along the y-axis, and one for the second diagram along the x-axis, and the third equation along the y-axis. To solve the problem, now we have this free body diagram, and for mass 2, the resultant force along the x-axis is the product of M2 and the acceleration. And then we are working now on mass 2 as if the first mass is not there, and then we set up the equation for the second mass, M2, along the x-axis. That is M2g sine theta, which is greater than t. Why? Because we considered the resultant force acting on M2 positive, and that is the direction of the acceleration. So the direction of the resultant force is in the same direction of the acceleration. Here, that's why m2g sine theta is the driving force that leads the two blocks to move in this direction. So the second step is just to substitute the values given in the problem, and here we will get the first equation. The second equation can be obtained from mass 1. This is the free body diagram for mass 1, and the force is acting along the axis where the resultant of the force along mass m1 is upward in this case, as long as the mass 2 is going down with the positive acceleration. This one is going up with the same acceleration as positive, consider. And here t is larger than m1g. That's why we have t minus m1g equal m1a. By also inserting all the values, we're going to get equation 2, solving these two equations for the acceleration, and we will get an answer of 1.76 meter per second square. Now another problem for a two-body acting along the y-axis, one of mass 2 kilograms, the other with 5 kilograms, and they are connected together by a rope sliding over a frictionless pulley. This system is called the Atwood machine. And if this system is released from rest, then we have a driving force for the 5 kilogram acting downward, and this will pull the 2 kilogram mass upward, obviously. So we have two free body diagrams, one for the first one for the 2 kilogram mass and the other for the 5 kilogram mass. Well, you are asked here to find the tension. Also, we can solve the problem for the acceleration as well. But we should notice here that once the 5 kilogram is moving downward, we're going to consider the acceleration downward with a positive sign for the 5 kilogram mass. This should be the same for the 2 kilogram mass, but working upward with the same magnitude as and a positive sign. So the whole line of motion is positive, with positive acceleration upward for the 2 kilogram and with positive acceleration downward for the 5 kilogram. This is a very important step towards solving the problem and setting the equations properly. Now, for the mass m2 with 2 kilogram along the line of motion upward, obviously the tension will overcome the weight of the 2 kilogram object, and we have along the y-axis we have the resultant force of m2a, and the forces acting to the left on the left hand side, t minus m2g. Again, t is larger than m2g because t is driving the mass m2 in the direction of the positive acceleration upward, or in the direction of the resultant force on m2 upward, if you like. Now, by inserting the given numbers or given magnitudes in the equation, we're going to get the first equation where we have two unknowns, t and a. Now we need another equation. We're going to get this equation from 5 kilogram mass. By looking at the free body diagram, we can easily tell that the 5 kilogram mass is moving downward in the line of motion with a positive acceleration, as I said before a while. Now, along the y-axis, the resultant force m5 times the acceleration equal to the sum of the forces, and the forces acting along the y-axis, m2g, which is the larger force that overcome the tension upward, and then we put in all the numbers given in the problem in order to get our second equation, also with two unknowns t and a. By solving these two equations, we're going to get an acceleration of 4.2 meters per second. Obviously, to get the tension, you just substitute this acceleration right away into equation 2, and you get a 28 Newton for the tension. You know, in the attitude machine, if you are asked just to find the acceleration and you forget about the tension, there is an easy way, an alternative way of getting the acceleration for this system. And that is by considering the two masses as one mass along the line of motion. And in this case, the sum of the masses as one mass multiplied by the acceleration is the resultant force for the system. What should we put on the left-hand side for the acceleration? Well, obviously, there are two competing forces along the y-axis, one pulling down, one trying to resist that and trying to put it to the opposite direction. So we have m5g trying to move in the direction of acceleration, and there is a weight trying to prohibit that motion. So these two forces are competing with each other. By doing that and substituting the values, you'll be able to get the same acceleration as before. That is 4.2 meters per second square.